Okay, so now we're going to talk about aqueous reactions. Aqueous reactions are going to be different because remember what I said, when in doubt, get to moles, right? So the difference between an aqueous reaction is that how we get to moles is going to be different. We're going to need to use the molarity of our solution, right? So when we started out with grams, we were able to jump to moles using the molar mass. But in solution, we're not starting out with grams. We're going to be starting out with the volume of a particular reactant, the volume of an aqueous solution. And in order to get to moles, we're going to have to use the concentration or the molarity of that solution. Okay, so the name of the game is pretty similar. The only difference is how we jump to moles is we use a different quantity. We use the concentration of the solution. Okay, so this, for example, would be relevant if we were doing one of these precipitation type problems, right? So we saw on our previous lecture from the last chapter, we talked about precipitation reactions. Using that solubility table, we could see that if we mixed a chloride solution with a solution of silver ions, we would get a precipitate of solid silver chloride. This is actually the net ionic reaction that's given here. Because I haven't pictured the spectator ions, so this could be sodium chloride and silver nitrate, for example, but then I went through and got my net ionic reaction. You could use either in order to get the mole ratios that you need. Okay, so the balance, you can, given the net ionic equation, we'll work with this. If all we had was the balanced chemical equation, we could work with that too. They give us the same information. Okay, so it wants me to determine how much of a 2.5 molar solution of silver nitrate, so the silver, is necessary to precipitate all the chloride from 2 liters of a solution, right? So of a solution in which the concentration of chloride ion is 0.0173 molar. There was an error in the slides where this was accidentally deleted, so I had to fill that in, but that's what that value should be. Okay, so we have 2 liters of a solution of chloride ions where we know the concentration of those chloride ions are 0.0173 molar. Okay, so we're going to start with those 2 liters of that chloride ion solution. Okay, now remember, much like when we have a molar mass, we convert that into a type of conversion factor. Same thing with our concentrations. When you think big M molarity, you want to think moles of whatever you're talking about over 1 liter. Okay, so this becomes 0.0173 moles of chloride ions over 1 liter, right? So this piece of information gets converted into a conversion factor that looks like this, right? Where I have moles over liters. Anytime you see that big M, I want you to think this type of conversion factor. Okay, so now I need to figure out how much of this silver nitrate solution I'm going to use. So my answer is going to be in a volume, right? So I'm going to need liters of silver nitrate or something like that. But in order to jump from moles of chloride to moles of silver, I'm going to need to use my balanced chemical equation, which tells me that 1 mole of chloride ions is consumed along with 1 mole of silver ions. Whoops. And now I can use the concentration of my silver solution. And again, when you see that big M, you think this type of conversion factor where you have moles over liters. Here, I'm actually going to have to put moles on the bottom. Take a second and convince yourself that you understand why that is. Because I need my moles of silver ion to cancel. And if I stop here, I'd be left with liters of this silver solution. So that's perfect. That's what I want. So I'm going to punch this into my calculator. And I'm going to find that I'm going to need 0.0692. Is that any more digits on there? Nope. Liters of this silver solution. All right, and that should all check out because my units will cancel out nicely, just like in all of our stoichiometry problem. The liters of chloride cancel, moles of chloride cancel, moles of silver cancel, and so I'm left with that volume of silver solution in liters. Paying attention to sig figs. Now here we got to be a little bit more careful because we got a lot more measured quantities going on. So I have both my volume, which has 3 sig figs, but I also have these concentrations that were given. Each of these, well, they all have the same number, so that makes it easy, I guess. But anyways, you have more measured values in here. Both the volume and the concentration can limit the number of sig figs. So you want to pay attention to that. In this case, we're at 3, and that's how many we have in our answer as written, so we're good. We would need 0.0692 liters of that silver solution. Okay, that would be my final answer. Okay, so very, very similar to what we've been doing all along, right? The difference is that the quantity of these reactants is given not in grams, which would require a molar mass, but it's given as a volume and a concentration. And I use that concentration to jump from liters or from volume to moles. But again, the name of the game is using this chemical equation. And in order to do this, I have to get to moles. Okay, so let's do part B here as well. I'm going to sort of erase just to give myself enough room. Okay, so determine how much of a silver nitrate solution, actually I'm going to get rid of my marking, my colorings here too. All right, so now we're at part B. Determine how much of a 2.5 molar silver nitrate solution is necessary to precipitate all the chloride from 1.5 liters of a 0.0435 molar barium chloride solution. Okay, so here they're trying to be a little bit tricky. All right, so let's take a look at what I mean by that. We know that we have silver nitrate, so silver nitrate is AgNO3, aqueous. And that's going to combine with barium chloride. I need to figure out what barium chloride is. So remember, when we're looking at our periodic table, we could figure out the charge on these ions. In the first column is +1. In the second column is +2. Go over to the other side. The noble gases don't form ions. The halogens are -1, moving over -2. So now I need to find barium and chloride. Here's barium and here's chlorine. So the barium ion has a +2 charge and the chloride ions have a -1 charge. All right, so what I mean by they're trying to be tricky is Ba2+ and Cl1-. That means that my actual compound will have 2 chlorides per barium. All right, and so this is going to form that solid silver chloride as well as aqueous barium nitrate. And so what I mean by they're trying to be tricky is this isn't balanced as it is. This isn't a 1-to-1 ratio like it was in the previous example when I was told the concentration of chloride ions. Now I'm told the concentration of barium chloride. And so I have to account for this fact that there's going to be a difference. It's not going to be 1-to-1 anymore. It's going to be 2-to-1. Right? I'm going to need twice as much of that silver nitrate solution as I am the barium chloride. Or rather, I'm going to, for per mole of barium chloride, I'm going to need 2 moles of silver nitrate. That's what I should have said. Okay, so then this is just going to change the mole ratio that we use in our balanced chemical equation. Other than that, we set it up pretty similar. We're going to start with the 1.5 liters of barium chloride. We're going to convert to moles using the solution concentration. So the 0.0435. Whoops, that's not how to do that. I was trying to put moles on the bottom, but of course that's wrong because then it wouldn't cancel. So I need to put it at the top. Moles BaCl2 in 1 liter. And then I can jump, now that I'm in moles of barium chloride, I can use my balanced chemical equation, which tells me 1 mole of barium chloride will be consumed along with 2 moles of silver nitrate. And then so now I'm in moles of silver nitrate. I need to figure out how much of that silver nitrate solution I'm going to use. And remember, we measure solutions volume. So I'm going to need to jump from moles to liters. So then I'm going to use this 0.250 moles silver nitrate in 1 liter. Okay, so this is going to be now my equation. Whoops. My equation. Punch that into my calculator, and I will see that I get 0.522. That's actually all the digits I get. I go through, cancel out my units, liters of barium chloride cancel, moles of barium chloride cancel, moles of silver nitrate cancel, and I'm left with liters of silver nitrate. I didn't really leave myself very much room. Okay, and so take a second and determine how many sig figs I should have in my final answer. My concentrations both have 3 sig figs, but my measurement, my volume of barium chloride only has 2 sig figs. So remember the rules for multiplication and division. I would only have 2 sig figs in my final answer, 0.52 liters of silver nitrate solution. This should be my final answer. I will just point out that I did make the sig figs different in this example that I'm doing than what the original lecture slide was, because I want you guys to practice doing sig figs. The lecture slides from the book always default to 3 sig figs or whatever, and we need to be on the lookout because that's not necessarily going to be the case, or they usually default to 3 sig figs. Okay, so that's not always going to be the case. In this case, this 2 sig fig measurement is what would limit me to 2 sig figs in my final answer. Okay, so let's do some more solution problems. So that would have been a precipitation problem. Another common solution problem is acid-base reactions, and we talked about those as well last chapter. Those also occur in solution. So I'm going to try to figure out how much of a 0.150 molar solution of sodium hydroxide is necessary to neutralize an acid. In the first example, we're going to do 275 milliliters of a 0.075 molar solution of HCl. So before I can do this, I need my balanced chemical equation first, right? So step 1 would be the balanced chemical equation. That happens when I react HCl with NaOH. At this point, we should be able to predict the products of our acid-base reaction. Remember, it's salt and water. It's a double displacement, so you're going to swap those cations. So now the sodium is paired with the chloride, and the hydrogen is paired with the OH, and that makes water, right? So that's what you should have in your head about acid-base reactions, is acids mixed with bases to form salts and water. And so that's what we see here. All right, and this is a 1-to-1 ratio because I had just 1 proton on my acid and only 1 hydroxide on my base. So now I have a balanced chemical equation. I can start doing my stoichiometry. I'm going to start out with what's given, the 275 milliliters of HCl. And I'm going to want to use my concentration, but my concentration is in moles per liter. So the first thing I actually have to do is jump from milliliters to liters. And you don't have to, have been doing this a long time, I know there's 1,000 milliliters in a liter. Remember, we also have our constants page that helps us go from these various metric unit conversions. So milli is 10 to the negative 3. You should be able to use these constants pages, right? These SI prefix conversions are one of the first things we did in the course. Okay, so now that I'm in liters, I can use my concentration, which says that there's 0.075 moles of HCl in 1 liter of this solution. And what I care about is what I want, or my answer is talking about NaOH. So I need to jump from moles of HCl to moles of NaOH using my balanced chemical equation. And now finally, I can get to talking about the amount of the solution I'm going to use in liters by using my concentration and 1 liter. Okay. So again, kind of just to point out here, these concentrations are being converted into conversion factors that look like this, where you're stacking moles over liters or liters over moles, right? In this first one here in yellow, we're going from liters to moles. And in this second one here in green, we're going from moles to liters. Okay, so punch that into my calculator and I will get 0.1375. Going to go back and pay attention to units. Milliliters will cancel out with milliliters. Liters will cancel out with liters. Moles of HCl will cancel. Moles of NaOH will cancel. And so I'm left with liters of NaOH. Right? I could convert it to milliliters if I want, but I didn't, right? So pay attention to your units, make sure everything canceling. That'll tell you what your units at the end will be. It didn't specify whether it wanted milliliters or liters, so I'm just gonna leave it in liters. All right, sig figs. Now I have to pay attention a little bit more than previously. I have to pay attention to my initial volume measurements, but also my initial, there's 2 sig figs there. Initial concentration measurements, 3 sig figs. So here I'm limited by this concentration of HCl, which only had 2 sig figs. So my final answer will only have 2 sig figs. So the amount of NaOH that I would need would be 0.14 liters of my NaOH solution. Okay. All right. So now let's move on to part B. I'm going to get rid of my coloring here so we don't get mixed up. Oops. All right, so now my acid that I'm going to use the same solution of base, but now I'm going to have 1.95 liters of 0.225 molar H2SO4. So again, before we can actually even do any stoichiometry, we need to go ahead and get our balanced chemical equation. So now we have our acid is H2SO4 plus NaOH gives us salt, which in this case would be Na2SO4, and water. Okay, this is not balanced yet. And in particular, I can see that I have now 2 hydrogens that are donated by my acid, not just 1. So I'm going to make 2 moles of water, and I'll have to balance that out with the amount of base that I need. And that should all balance out. So this right here, this 2, means that you have 2 donatable protons compared to just the 1 on my HCl. This is what we call a diprotic acid, meaning it has 2 hydrogens. So it's going to take 2 equivalents of base to neutralize. There's also a triprotic acid, phosphoric acid, that would require 3 equivalents of base to neutralize. Okay, so pay attention to that subscript on the acid. All right, other than that, the setup's pretty much the same. I'm going to start with the amount of acid that I have, 1.5 or 1.95 liters of my H2SO4, my sulfuric acid. I don't need to convert to liters because I'm already in liters, so I can just jump to the concentration step. Oops, 225 moles of H2SO4 in 1 liter of that solution. And now I can use my balanced chemical equation to jump from moles H2SO4 to moles NaOH, where I have 1 mole of H2SO4 will react with 2 moles of NaOH. And so if I stop there, I'd have how many moles of this solution, or how many moles of sodium hydroxide I need. But what I really want is the volume of that solution of sodium hydroxide. So then I'm going to jump from moles of sodium hydroxide to liters using that concentration. Okay, so punch this into my calculator. Again, I want you guys to try to get into the habit of just running it all in one line. It will make it, will make it a lot easier to avoid making silly mistakes, easy mistakes to make. And so what we get is 5.850 mole, oh, not moles, sorry. 5.850, or really the calculator would just spit out 5.85. I go through, liters cancel out, moles of sulfuric acid cancel out, moles of sodium hydroxide cancel out, and so my units is liters of NaOH. And then sig figs actually already kind of work themselves out. I have 3 sig figs for this number, 3 sig figs in this concentration, and 3 in this concentration. So that's correct as I've written it. So 5.85 liters of that sodium hydroxide solution would be necessary.